You're here ready to cut through the noise, and that's exactly what we're about to do today.
Mm-hmm.
We're diving deep into something that's really shaking up how we think about running these massive AI models, large language models, LLMs.
Right, the big ones.
Yeah, the powerhouses like ChatGPT, but getting them to run efficiently, that's a huge hurdle. Often needs, well, expensive specialized hardware.
It really is a fundamental challenge. The scale of computation these things need, it can limit who gets to use them, and the energy cost is frankly significant. Efficiency isn't just nice to have anymore.
It's becoming essential.
Absolutely.
And one really fascinating approach tackling this is the rise of one-bit LLMs. Think of it as radically streamlining these models, right, for speed, lower resource needs.
Exactly. And leading the charge here are concepts like BitNet and, maybe more importantly for today, BitNet b1.58.
BitNet b1.58.
Yeah, for those tracking the technical side, the bit part refers to the precision of the model's weights, its parameters. Standard models use higher bit counts, for more detail.
More nuance.
Right. But cutting this down to just one bit, or well, closer to 1.58 bits with the ternary values in BitNet b1.58, that leads to a dramatic drop in model size and, crucially, the cost of inference.
Okay, let's zero in then. We're not just talking theory today. We are dissecting a brand new tool from Microsoft Research. It's called BitNet.cpp.
BitNet.cpp.
And our mission to really understand how this thing makes running those super efficient ternary BitNet b1.58 models, how it makes that a reality on like your everyday CPU.
Uh-huh.
We're going to unpack the core innovations driving its performance and, why they actually matter.
And we've got a solid base for this. Our insights are coming straight from a detailed research paper by Microsoft themselves, outlining the development, the testing,
Yeah.
the evaluation of bitnet.cpp. And we also have your detailed notes analyzing that work. So it gives us a good vantage point, I think, on the academic side and the real world results.
Exactly. Forget just the summary. We're going straight to the heart of what makes bitnet.cpp feel like a pretty significant leap forward in efficient AI. So let's start with the basics. What is bitnet.cpp really?
Okay, at its core, bitnet.cpp is a highly specialized software stack. Think of it like a finely tuned engine.
Okay.
Its main purpose is enabling rapid, and this is critical lossless inference of these ternary BitNet b1.58 LLMs directly on standard
Right,
CPUs.
correctly on the CPU.
Yeah. The ambition here is really to unlock the potential of these one-bit LLMs, make them practical for, widespread use in typical computing setups.
Lossless interest. Okay, we definitely need to circle back to that point. That sounds important. But first, how does it manage this performance on just regular CPUs? What are the sort of key innovations inside bitnet.cpp?
So the central advancements are really in its suite of highly optimized kernels.
Kernels, right.
These are the basic building blocks for computation in the language model. And bitnet.cpp gives you several Taylor kernels, each using kind of unique strategies to maximize efficiency. Understanding these is key to appreciating what's new here.
All right, let's get into the specifics then. First up, you mentioned the I2S kernel. What's the core idea, the innovation with that one?
So the I2S kernel uses a conceptually straightforward but still effective innovation. It's focused on cutting down memory bandwidth needs.
Okay, memory bandwidth.
Right. It does this by converting the LLM's full precision weights offline before you run it into a 2-bit representation.
2 bits.
Yeah, this compressed format seriously reduces the memory footprint. Then, during the actual computation, these 2-bit weights get unpacked back to their original precision, but only just in time for the standard matrix multiplication.
Ah, so the innovation is using that compressed format for storage and transfer, reducing the memory bottleneck during inference. It's kind of like using zip files for moving data, but unzipping right when you need it.
That's a great analogy, exactly. And this trade-off, it's particularly good when memory bandwidth is the main limitation.
Right.
The researchers also suggest using the I2S kernel with enough CPU threads. This lets the compiler use instruction-level parallelism to speed things up even more after the weights are unpacked.
Okay.
So the innovation is really that combination, efficient compression decompression plus maximizing parallel processing.
Interesting. Optimizing data movement, then using standard compute power. Okay, now let's move to the TL1 kernel. This one sounds like maybe a more radical optimization.
It is, yeah. The TL1 kernel's core innovation speeds up the matrix multiplication itself using a pre-computed lookup table, or LUT,
A lookup table?
based on pairs of weights. So instead of directly calculating the multiplication for every pair of weights, TL1 packs these two weights into a single 4-bit index.
4 bits for 2 weights. Okay.
And that 4-bit index points directly to pre-computed results stored in an integer lookup table, specifically in 16. And critically, the activations that correspond to those weight pairs, they're also pre-computed and stored in the LUT.
So the big idea here is swapping complex math multiplication for much faster table lookups and just simple addition, training pre-computation and some memory for runtime speed.
Exactly right. During the matrix vector multiplication, which is fundamental in neural nets, TL1 is essentially just doing lookups in this pre-calculated table and adding up the results.
Much less computationally heavy.
Drastically less intense than the direct multiplication in I2S. And the researchers, they connect this back to earlier work, specifically something called TMAC by Wei and others.
Okay.
That work pioneers this LUT-based method for low-bit LLMs on CPUs. TL1 adapts and optimizes it for BitNet b1.58's ternary nature, and they found TL1 is especially good for larger models when you don't have many CPU threads available.
Got it. So TL1's innovation is transforming the core math using pre-computation and LUTs, especially good when parallelism is limited. Now, what about TL2? How does that push efficiency even further?
TO2 builds on TL1's core idea, the lookup table, but it pushes the compression even harder. Its key advance is packing triplets of weights into just a single 5-bit index.
3 weights and 5 bits. How does that work?
Well, that 5-bit index cleverly includes a 1-bit sign. By encoding more weight info into a smaller index, TL2 gets an even higher compression ratio than TL1.
Wow.
Which means even lower memory footprint and bandwidth needs.
Compressing 3 weights into roughly the space used for 2 before, that's a big jump in data density. The innovation seems to be just maximizing information per bit.
Precisely. This higher compression means less data movement during computation, which is vital in resource-constrained situations. Like TL1, it uses a pre-computed LUT. The researchers highlight TL2's benefits when memory or bandwidth are the absolute main bottlenecks, even if the indexing gets a bit more complex.
So we have these 3 different kernels, I2S, TL1, TL2, each with its own smart way to speed up and compress these 1-bit LLM calculations on CPUs. Now, how does this actually translate to real performance? The paper must have some compelling results.
Oh, definitely. They did a thorough evaluation of BitNet.cpp, focused on 2 key things: inference speed tokens per second and energy efficiency joules per token.
Right, speed and power.
And they tested BitNet b1.58 models across a really wide range of sizes, from 125 million parameters up to a massive 100 billion.
100 billion parameters, that's huge. And they tested on different CPU types, right, to get the full picture.
Exactly. They used an RM-based Apple M2 Ultra, sort of representing modern, power-efficient chips, and an x86 Intel Core i7-3700H, a common high-performance laptop-desktop CPU.
Good comparison.
Yeah, let us see how BitNet.cpp performs across different standard hardware.
Okay, let's talk speed then. What kind of gains did they actually see compared to, say, llama.cpp?
The speedups were pretty substantial. On the Intel x86 chip, BitNet.cpp was anywhere from 2.37 times up to an impressive 6.17 times faster than llama.cpp.
Whoa, over 6 times faster potentially?
Yeah, and interestingly, the larger models generally saw the biggest gains, which really highlights how well these optimizations scale up.
A potential 6-fold speed increase. That's genuinely disruptive for running LLMs locally. What about on the Apple Silicon, the M2?
On the Apple M2 Ultra, the speedups range from 1.37 times to 5.07 times faster. Again, bigger models tended to show greater relative improvement.
Still very significant.
Absolutely, but maybe the most striking result was achieving near human reading speeds, think 5 to 7 tokens per second, even when running that 100 billion parameter BitNet b1.58 model on a single Apple M2 Ultra CPU.
Wait, reading speed on a 100 billion parameter model using just the CPU. That's kind of astonishing. That really changes the game for accessible AI, doesn't it?
It really does, and the researchers also looked at hardware memory bandwidth. They noted the M2 Ultra has higher bandwidth than that particular Intel i7.
Ah, okay.
And that likely helped explain the even more pronounced speedups for large models on the Apple chip. It shows how the software optimization and the hardware capabilities work together.
Makes sense. Good software takes better advantage of good hardware. Now, speed is one thing, but energy use is also a huge factor, especially for wider deployment. How did BitNet.cpp do on power efficiency?
This is another area where BitNet.cpp really shines, another key innovation, really. They measured the energy used per token generated very carefully. On the ARM-based Apple M2, they saw energy reductions between 55.4% and a really remarkable 70.0%.
70% less energy.
Yeah, with the larger models showing the biggest savings.
Cutting energy use by up to 70%, that's massive. Huge implications for battery life on devices or just the overall environmental cost of AI.
Absolutely. And on the x86 Intel CPU, the energy savings for the smaller models they tested were even more dramatic, ranging from 71.9% up to 82.2% less energy used.
Wow, over 80% on some configurations.
Yeah. They didn't have energy data for the absolute largest model on Intel, but the results strongly suggest BitNet.cpp is incredibly effective at cutting the energy footprint across different CPUs, especially maybe for smaller models on those high-performance cores.
So it's not just faster, it's way more energy efficient too. That really boosts the case for running these advanced models locally. Okay, let's go back to that term you flag, lossless inference. Does getting all this efficiency come at a cost? Does it hurt the accuracy, the quality of the model's output?
This is where BitNet.cpp, I think, truly stands out. It represents a major innovation in efficient AI specifically because of this. The researchers were rigorous here. They used 1,000 prompts from the Wildchat dataset,
Okay.
and they compared the output tokens generated by BitNet.cpp against a full precision FP32 kernel that's kind of been gold standard for accuracy. And they also compared it against the accuracy of kernels in Llama.cpp.
And the verdict on accuracy. Is there a trade-off?
Remarkably, no. The key finding is that BitNet.cpp achieves 100% lossless inference for these ternary BitNet b1.58 LLMs across all three kernels, I2X, TL1, and TL2.
100% lossless. You mean the output was identical to the full precision model?
Identical token for all the prompts they tested, which is a stark contrast to the llama.cpp kernels they evaluated. Under the same strict matching conditions, llama.cpp only achieved about 1.4% accuracy.
100%. That's actually groundbreaking. It completely challenges that common assumption, right? That extreme quantization always means losing some accuracy. This suggests the innovations inside BitNet.cpp have somehow managed to overcome that fundamental hurdle.
Precisely. It directly addresses one of the biggest worries in model quantization. Being able to keep perfect fidelity while getting these huge speed and energy gains, it's really a testament to the clever design of BitNet.cpp and its kernels.
This is all incredibly exciting stuff. The paper also mentioned future work, right? What's next for BitNet.cpp in this whole one-bit LLM area?
Yeah, they outline several promising paths forward. A big focus is expanding platform support, getting BitNet.cpp running on more hardware mobile devices, smartphones,
Phones.
and also specialized AI accelerators like NPUs and GPUs. That would really democratize access even further.
Bringing this kind of efficiency to mobile would just unlock tons of new on-device AI possibilities. What else are they looking at?
Another really critical area is optimizing how these one-bit LLMs are trained. Right now, training these super quantized models effectively is still an active research area.
Right, training is different from inference.
Exactly. Better training techniques are crucial for wider adoption. And finally, they're really interested in the idea of co-designing hardware and software specifically for this one-bit approach.
Building chips specifically for this kind of math.
Yeah, that synergistic approach could unlock even bigger performance gains down the line.
It definitely sounds like we're really on the edge of a major shift in AI infrastructure. And BitNet.cpp seems to be playing a key role in making these advanced models more accessible, more sustainable.
Absolutely. Those novel kernel designs specifically optimized for one-bit quantization, that's a significant contribution.
So for you, our listener, the key takeaway here really seems clear. BitNet.cpp is this remarkable tool. Through its innovative kernels and the, frankly, extreme efficiency of one-bit quantization, it's making it possible to run powerful LLMs on your regular CPU with speed and energy efficiency we haven't really seen before.
And the truly surprising part, maybe, is hitting near human reading speeds for those massive 100 billion parameter models on standard CPUs. It really redefines what's possible for local AI, cutting the dependency on high-end GPUs for a lot of inference tasks.
The real ha moment for me is proving that 100% lossless inference is possible with such extreme quantization. It just fundamentally challenges that assumption that efficiency must cost accuracy. BitNet.cpp shows that with smart architectural design, you might actually get both.
Which raises a crucial question for you listening. What are the potential impacts of this technology for your work, your interests? Is it faster local processing, lower energy costs for AI, or just being able to play with cutting-edge models without needing specialized hardware? BitNet.cpp opens up a whole range of really exciting new possibilities.
Exactly. So as you think about those implications, here's one last thought to maybe chew on. If a 100 billion parameter model can run this efficiently on a CPU today, what other groundbreaking advances in AI infrastructure might be just around the corner? Further blurring those lines between cloud computation and what we can do locally. The world of efficient AI is moving incredibly fast, and BitNet.cpp gives us a fascinating peek at what's coming. Thanks for joining us for this deep dive.